So what we're going to cover in this episode, this video, is we're going to look at something called single slit interference. We're going to have another look at the double slit interference that we did a couple of weeks ago, again, and maybe completing the derivation properly this time. We're going to look at diffraction gratings, which are very similar to this, just lots of slits. And we are going to then finish off with something called thin film interference. Now I'm going to leave it up to you how you do this. You might want to try a little bit of theory and some questions and then continue to finish, or you can try and understand as much of the theory as you can and then do all the questions at the end. It's up to you. So let's begin. So to start with single slit interference, we're going to be talking about something called Huygens principle. I'm not sure how to pronounce it, but it's something like that. It's not necessary for you guys to understand it fully, but if you are left with a few doubts and you need it to understand it, then I suggest you go onto the slide presentation and you watch an explanatory video that will deepen your understanding of it. Like I said, it's not on the syllabus necessarily, you just need a little bit of a reference. So I'll leave that up to you. Now we've come across diffraction before. Diffraction is the spreading of waves as they go through a gap, which is similar or smaller than the incident wavelength. But what we find is there's some very specific and very strange situations where you don't just get the spreading, but you actually get interference taking place. And you get areas of constructive and destructive interference. So we're going to look at that in a little bit more detail. And this is the setup you would use to try and investigate this effect. And we'll definitely dig this out in the lab at some stage in the lesson so you can see it. But what you have this time is a single slit, not the double slit that you used last time we did this experiment. You need monochromatic light, laser. And as you aim very, very carefully for the single slit on a screen, you should be able to see a very, very bright fringe in the center, followed by some dark fringes here, and some other repeated bright fringes. It's similar but different to the double slit interference pattern we got, but we'll compare them a bit later. So what you actually end up with is something like this. One intense, very strong bright fringe in the center and repeated patterns of dark and light. And so here we have a really nice illustration of this. We have a small gap, very small gap, and you get a nice curved diffraction pattern. But there's this key situation where you start to perceive the constructive and destructive interference. So single slit diffraction focuses on this situation, interference due to a single slit. Now, why on earth does that happen? Now, in order to understand how it works, we need to think about something called Huygens principle. Huygens pronounced the American way. I'm not sure how to pronounce it in Dutch. But what he stated was stipulated at the time, which helped understand an awful lot of wave-based phenomena, was that you need to consider diffraction as not a sequence of waves, the way that we've looked at them before, like this, like wave fronts, but to consider an infinite amount of point sources. So according to Huygens' principle, each point on the wave front can be thought of as a source of a spherical wavelength. So the reason why we get this spreading out is because when you consider all these individual wave spreads, these spreads, so you can see this one spreading out, what happens when they all sequentially, like constructively interfere with each other, is you end up getting this wave front. which is just basically adding them all up together. Now, why this helps with the interference patterns is it allows us to build a model for lots of interfering sources. Like I said, you can go back to the video and do a bit of research if this is something that interests you. But for now, you don't actually need to take this any further, because the model allows us to look at diffraction patterns like this. So if we take, for example, in this gap here, and we place our model of 1, 2, 3, 4 point sources, each emitting a sequence of waves, you can see that there is, thanks to these diffracting point source patterns, we can see that they constructively and this would be destructively and constructively interfere with each other. They also account for the particular nature of the diffraction pattern for a single source, which has a very strong, intense peak in the center opposite the gap, and then the repeated and smaller intensity patterns of the other peaks at either side. Okay, but I'll come to that in a minute, because you do need to be able to describe the intensity pattern in a lot of detail. So now let's go and do some maths. So what we're going to try and do is come up with a relationship that will allow us to look at these diffraction patterns in a bit more detail. What you've got here is a simplification of what's going on at the gap. You have a gap of size B, we'll call it, and we're looking at the light leaving the extreme positions of the gap. Now, it's important to define our path difference. These lines should eventually meet. They're parallel to each other, and the reason why we are allowed in the physics sort of way to draw them parallel to each other is because the distance that they actually meet is very, very far. So we're considering a situation where the slit and the screen are very far away from each other. So if you have one ray like this and one ray like that, I haven't drawn it very well, but basically the further away or the bigger this distance d is in comparison with this distance here, the closer to parallel they are. So in reality, when we look at this diagram and we make this assumption that the angle theta here is equal to this angle, we are only allowed to make that assumption because we are assuming that d is very large. This is otherwise expressed by sometimes calling this angle up here some variation, and an approximation is allowed. So you would say theta dash equals theta. Okay, so I'll just say that again. These two angles are assumed to be the same only because our distance d is very large. So what happens when these two meet? They would constructively interfere or destructively interfere depending on this path difference. Now let's do a bit of background theory. If this path difference, the difference in length of this wave and this wave, if that path difference is lambda, then what you get is constructive interference. And if it's lambda over 2, it becomes destructive. Okay, so we're considering destructive interference at this point here. So we'll be looking at this phenomena when the path difference here is equal to lambda over 2. So that gives us the beginning of something. Now we're going to look at this a little bit differently, however, in the light of the relationship that we came up with for Young's double slits. Now, in order to fully carry out a derivation using Huygens principle, we need to refer to our double slits idea. When we have a double slit situation, we were dealing with a distance between two slits. So we would say the center of one slit to the center of another, and that was our distance x. Actually, I think we definitely refer to it as d. Okay, so that was our distance d. What we're going to be looking at here, though, is we're going to be treating our wave fronts. We're going to be looking at the interference patterns as if they were coming from exactly the same as the double slit situation. We're going to be looking at two arbitrarily chosen points in that slit. Now, the best way to think about this is if we divide that single slit into two. So imagine that we have these two gaps, one gap and two gaps. So what we'll do is take a point in the center of this gap and a point in the center of this gap. And now our distance, our width distance, is equal to W over 2. So now we're going to consider the path difference between the waves that travel from this point and the waves that travel from this point, eventually converging at a distance very, very far away and destructively interfering. Okay, so that's better. So here we have the two parallel rays which eventually meet here, and there's a path difference. Now, before we draw the path difference, let's draw the angle to the center. Okay, and as previously stated, that same angle is here. Now, what's really important about this point is the path difference. This bit here, which we've already seen, has to be lambda over 2 in order for destructive interference. So what exactly is that path difference in terms of the gap size? Well, we can write it over here. We can see if that is theta, W2 sine, because it's the hypotenuse of that triangle, and we want to find the sine of it, sine of the angle would be equal to lambda over 2 to give you destructive interference. And in order to simplify that, we would end up getting rid of those two. And then if you remember, for very, very small angles, and this is indeed a very small angle, sine of theta equals theta. Okay, so what we end up with is this. Now, for some bizarre reason, because I've read this in so many different textbooks in my life, I've mixed up W with B. Okay, so this should be a B. Okay, so now it makes sense and it fits the book. Let me change it on here as well. So this should be a B as well. And it fits what it says here. The angle for the first minimum of a single slit diffraction pattern is lambda over B. This is not on the data booklet. Okay, so you can just learn it, or you can understand the derivation, which potentially could come up, not in a complete form, but maybe broken down. So it's important that you do understand it. Okay, so here is our diffraction pattern question. Now, this can be expanded, and I'll tell you in what direction. Sometimes you're given a completely different piece of information. You're not given the angle at all, but you are given this width here, S, the distance from the central maxima, or the central bright bit, to the destructive, or the point of destructive interference. In that case, you can easily find the angle by using the idea that tan of the angle is equal to the angle. It's the same thing. It's because it's so small, and we are dealing with radians, remember, equals S over D. So this could be placed in addition with that. So you could end up with lambda b equals S over capital D. Now that's not in the data booklet either, but it's also very common. Now the relative intensity angle graph for a single slit diffraction is as follows. Very important that you are familiar with it because it doesn't look like any of the others. It has a very, very big peak of relative intensity. And then the minimums, which you can see on the x-axis reads angle, okay? The minimums are evenly spaced at equal intervals, which are highlighted here, and you could be asked to actually put some numbers to them. So as long as you remember that the difference between them is the same, once you have the angle of the first destructive interference, then it's quite easy to place the next, because it would be 2 times that angle, which is twice the wavelength over b, the gap thickness, etc. Okay, so make sure that you learn that. You can stop and try some questions now, or continue and fill your head with more facts. The following section is a bit of review, actually, even though we've done it before. We're going to look at interference again. Path difference, you should be clear on the path difference between 2 waves that are constructively interfering, okay, is n lambda. Now n is an integer depending on which bright or constructive fringe we're looking at, and I'll define that in a little bit more detail in a moment. The condition for destructive interference, therefore, would be the same plus a half, because that's when you're going to get a destructive situation where you are half a wave out of phase. Okay, so these are the conditions. You have n lambda for constructive and n plus a half lambda for destructive. And if you see it on a wavefront diagram, you'll see what I mean by which fringe we're discussing. So you tend to have something called a 0 order maxima in the center. So 0 order maxima is in the center. Then you will have a destructive fringe. These are also called fringes. And then the next would be your first order maxima on both or either side. Order maxima on either side. So in the center, this is how you label these correctly. You have your 0 order maxima, and then you have your first, and etc. You would have your second, third, and these would be on either side. Young's double slits you've come across before, so let's review and look at that formula in more detail. Already, if we look at the fringe pattern for Young's double slits, we can see that there is a palpable difference. You don't get this thick white line in the center. You actually get quite a regularly spaced set of fringes. So let's have a look at that. And now let me review the derivation that I did on the board the other day, but I don't think I did it particularly well. So I'm going to go over it again, though you may not need to, so you might want to fast forward if necessary. Now the relationship that you guys derived was this one. This is the one that we've been using. It does look a bit different, darn it, because these books never agree. So that should be an S. Okay, so I'll write it under here. S equals lambda D over D. Okay, so that's the formula that you are using, the one in the formula booklet. So let's go over how we get to that. So this is our diagram showing how the lines space out to constructively interfere. So what we're going to be looking at now is constructive, and it makes sense to do that with these fringes because they are equally spaced out and equal in intensity, whereas in the previous example in single diffraction you're evenly spaced and similar fringes with the dark fringes, and that's why we looked at destructive. We're safe to look at the constructive because it's homogeneous, it's similar. So if we take a constructive fringe over here, we look at the angle from the center to that fringe, and we're going to call it theta. It's equal to this point here, but only because we are making the assumption that this angle and this angle is equal, and we can only do that because this distance is very big compared to this distance. So we're making an assumption. That angle is clearly not the same as that one, but the difference is so small that it doesn't actually affect the mass to the range of certainty that we're using. Okay, so enough of that disclaimer. Let's have a look at this point here. Now, why are we getting constructive interference? Because this wave is a multiple of a full wavelength shorter than this one. So this distance here, which is actually d sine theta, is equal to some function, some whole number, n lambda. Now, we already know from maths comes and saves us, that sine of that angle is the same as theta itself because the angle is very, very, very small. So what we have is d, I'm going to put it here, where should I put it? I'll put it here, d theta equals n lambda. Now, we could use it as is, or we could try and come up with a better, more measurable version of theta, which would be this distance, which we should call s, by the way. So s over d becomes theta, because s over d would actually be tan of the angle, but for very small angles, tan of the angle equals the angle. So tan of the angle equals s over d. So if we put this in here, we end up with, again, I'm running out of space, let's put it here, d s over capital D equals n lambda. Okay, now most of the time the n is 1 because we're just looking at the first maxima, the first order maxima. But in this case it would be 1, 2, 3, 4. It would be n equals 4, and the angle that you're dealing with is actually, the angle to the third order, 1, 2, 3, fourth order maxima there. So if we sum up in a slightly tidier fashion, we have a phase difference of d sine theta, which is equal to n lambda, some function of lambda. Because sine theta is the same as theta, we end up with d theta equals n lambda. And because of the triangular nature of the setup, we end up with d s over capital D equals n lambda. Now that formula can be used at any stage of its derivation. So n lambda equals d sine theta you will also find very useful, and it's important also to consider that your destructive interference will happen when n plus a half lambda equals d sine theta. Okay, so these two might be useful. Now let's have a look at our intensity angle graph, very different to your single slit intensity arrangement. And once again, you are required to learn it off by heart. So what you can see here is there isn't a defining central peak. They're all similar. In fact, they're the same. It's just there is an attenuation. There is a decrease in amplitude as we get further and further away. But it's slight. It's a slow one. You don't get this huge drop that you get with the previous situation. And in fact, you can sort of superimpose those two together. This is a slightly more complex situation, but I wouldn't worry about it too much. You end up getting your single slit diffraction envelopes superimposed over your secondary. But I wouldn't worry too much about this for now. Okay, so you have some questions coming up. Give it a go. Maybe try one or two before moving on. So the story does not end with 2 slits. You can have as many slits as necessary. And in fact, a diffraction grating is a filter arrangement which has a huge amount of slits in them, and it has some really interesting effects. Now, as you can see, there are some specific changes to your fringes as you increase the number of slits, and you can see them here. The slits become much more defined, clearer, but less wide as you increase the number of slits. Now, I'm not going to go into too much detail on deriving yet another formula, because in the end you actually end up with the same situation. The same formula applies. Some integer value times lambda equals d sine theta. And this is just as applicable to whether you're using 3-slit, 4-slit, or a diffraction grating. Now, let's look at a diffraction grating in a little bit more detail. So what's a diffraction grating? A diffraction grating is a filter which has an obscenely large amount of gaps or slits. So for light, monochromatic light, there'd be of the order of 300 or 400 lines per millimeter. Now, how does this change the way that you would work out your constructive and destructive interference? Well, in working out D, now if you remember, D is the distance between gaps, you would use this information to try and calculate your gap thickness. So if you have 300 lines per millimeter, you would then have 1 millimeter, 1 times 10 to the minus 3 meters, and divide those by a 300 to find that gap width. Okay, so bear that in mind for questions. Apart from that, everything else is pretty similar. Now, as we mentioned before, as you increase the number of gaps, you become, or you create maxima, which is much sharper and more intense. So when you use, for example, a double slit, you can see that you have a low intensity but a very wide peak. As you compare that to a diffraction grating, you have a much more intense but very thin and sharp number of slit. Now, this enables you to have some very, very clear differentials for light of different wavelengths. So, for example, if you're using visible light, you can easily differentiate the blues from the reds because they each line up in the correct position and they don't overlap because their distribution is so much smaller. So say, for example, you had visible light going through double slits. Both the red and the blue would position themselves in slightly different places because they have different wavelengths. Now, that difference is intensified with the diffraction grating because you don't get so much overlap. So you would get a distinct blue peak and red peak, I should say red peak and blue peak in different positions. And this allows you, and this would be how you would use diffraction gratings to identify spectra of different wavelengths. And I think this diagram does a much better job of showing how this happens. If you have white light, which is a collection of rays of different wavelengths incident on a diffraction grating, then you'll get your central white maximum. But then at your deviation, if I write the formula here, d sine equals n lambda, as you can see from here that your wavelength is proportional to the angle. So the bigger, and it's important you remember this, especially for multiple choice questions, but the bigger that wavelength, the bigger the angle. So red, which is bigger than blue, would have a greater angle, and so therefore would spread to a higher degree than the blue. And this is kind of the effect that you get when you look at white light through diffraction gratings. So hopefully I'll have that set up so you can have a bit of a play and have a look at them. So this is the last section, thin film interference, and it's a different kind of interference, it's a different phenomena, but it's the same principle of looking at path difference. Now, thin film interference happens when light reaches a coating of thin transparent material where there are reflection and refraction effects taking place. Now, the perfect example of these are bubbles that give you these pretty rainbow effects, oil on concrete, and interestingly enough, butterfly wings. So there you go. So let's learn a little bit more about thin film interference. So on a basic level, when light hits a transparent substance, it has two choices depending on the relationships between the two materials involved. But let's consider just this simple situation of light travelling from air into a thin film of oil, for example, on a floor. What you're getting is the first stage when it hits the boundary between air and oil. You're getting an initial reflection at 1. Then what's left of the light that doesn't reflect, it continues straight in through to the oil to hit the surface, where once again there is another change in density, and so therefore the light reflects again. Now there are other effects involved. Some of the light would be absorbed into the surface, and of the light that reflects back out, some of it gets reflected inside here as well again. But we're just gonna completely ignore those two. We don't like those, so they're not relevant, and they're not going to help us, and they'll just make things even more complicated. So we're just going to consider those two boundaries and those two phenomena: the light reflecting off that first surface, and the light continuing and reflecting off the bottom surface. Now what happens if these two rays of light, which are drawn to be parallel, but really once again, we've come across this before, but once again we're assuming that the distance at which they are meeting again is very large, so therefore they do constructively or destructively interfere. So what we've got once again is this path difference. If the distance here, that this ray 1 is travelling is some function of the wavelength bigger than the ray that bounced off in the first place, then there'll be constructive or destructive interference. Now I wish that was the whole story, but it's not. there's one little fact we need to add. So there we go, fundamental factoid coming up. A ray of light reflected by a material with an index of refraction greater than the one it was travelling in changes its phase by 180 degrees. Okay, I'm just going to wait for that to sink in. So if we have a look at this picture again, what it's saying is that this wave, as it bounces off a more optically dense medium, will change its phase by half a cycle. And the wave that continues on will do the same once it hits the bottom surface and then reflects back out. So these two will be in phase, constructively interfering, because this one has gone out of phase once and so has this one. So let's try and see that in a format that's easier to understand. Now, luckily for the IB, you only need to think about light that is incident normally. Now, if you remember, that's 90 degrees to the surface. So it makes it much easier to think about. So as that light comes into the denser material, I'm going to call this material A and this material B. And I'm going to put, let's see, if we move this all down here, I'm going to put the I here, and that's where the constructive and the destructive interference will take place, and where you perceive it. Okay, so the light is going to come into the denser material, it's going to reflect. I'm going to express it at a bit of an angle so you can see it, and it will constructively and destructively interfere at some point, which is very, very, very high above the surface, in order to make all the maths easier. So let's have a look at what's going on here. You've got a distance d, which is equal to the thickness of the film. Okay, now 2d is the total distance it's travelling, and that's going to be equal to some multiple value of the order associated with the order of the constructive and destructive interference. We're going to call that m, plus a half times lambda. Now the half, remember, is because of the phase change as it hits that boundary. Now when these conditions are met, you get constructive interference at the eye. And you would see an area of bright colour, like this one. What colour you see depends on the individual wavelength. Now, the wavelength that we're using in this calculation, however, is the wavelength in the material, so it would be lambda in B. And we don't want that. We want to express this in terms of lambda in A, the incident wavelength. Now for that we need to go back to our refractive index theory. If you remember, you had V1 over V2 equals lambda 1 over lambda 2, which equals refractive index of material 2 over refractive index of material 1. Remembering this is material 1 and material 2. So if we express lambda B or lambda 2, as I've written it now, foolishly, lambda 2 is equal to lambda 1 N1 over N2, refractive index of material 1 over refractive index of material 2. Remembering that if the material, the incident material, is air, then N1 becomes 1. So now we have lambda 2 equals lambda 1 over N2, which is the refractive index of the material. So if we go back to our original formula, then 2D now becomes equal to m plus a half lambda 1 over the refractive index of material 2, which leads us to our full relationship of 2nd equals m plus a half lambda 1. And these are the relationships given in the data booklet. Now for constructive interference, 2dn, 2 times the thickness of the film times the refractive index equals m plus a half lambda, and destructive interference would be the case where you don't have this half phase difference, and so therefore you get destructive interference.